Hey everyone, welcome back to the series on solid principles, the 5 key rules that help you write clean, maintainable, and scalable software. Today we are diving into the last one, the D in solid, the dependency inversion principle. Let me start with a simple code example. Let's say you have two classes, user service and email service. Let me call email service from user service. For that, what you have to do, we have to instantiate the email service class and call send email. Okay, now here, what do you see? User service is dependent on email service, right? Why? Because user service is creating the instance of email service and calling it directly here. It means without email service, user service will not be done, right? It also means that if email service changes or breaks, user service might break too. For instance, say someone decides to add subject and body parameters to make the email more flexible and changes the email service to take the subject and body, maybe to support templated emails. Let me make the changes and show you. Let me pass on subject and body. Perfectly reasonable, right? Let me build it. See, now user service won't compile. There is an error. Any idea why this error is? Because the user service was tightly coupled to email services. Can you see here the new keyword? This shows how dangerous tight coupling can be. Even small changes in the low level module ripple up and break your high level business logic. Now imagine this happened in 20 different places across the app, all using email service directly. That's a lot of refactoring, testing, and risk, all because one low level class changed. That's exactly the pain the dependency inversion principle is trying to save us from. You must have seen such dependencies. These are there everywhere in the applications. And you know what? If these are not handled properly, your app becomes a nightmare to maintain. So, what's DIP? Dependency inversion principle is all about how we manage dependencies in our code. Let's look at the definition. High level modules should not depend on low level modules, both should depend on abstraction. Abstractions should not depend on details, details should depend on abstraction. So it has two parts. The first one, high level modules should not depend on low level modules, both should depend on abstractions. And the second part, abstractions should not depend on details, details should depend on abstraction. Let's break it up. Let's look at the first part. Before we move further, perhaps it is good to understand what's high level module and low level module. In simple terms, high level modules are the ones that contains business logic like order service, registration service, inventory manager, and low level modules are utility classes like payment processor, email sender, database connector. Now the problem is high level modules often create or call these low level modules directly. Something like this. This creates what we call tight coupling, meaning the two classes are glued together too strongly. If one low level class changes, like we added subject and body, the high level class may break. If you want to replace the low level class, you will have to go hunt through the high level classes and make changes there too. Please understand, in real time it is possible that it is not one class that is using email services. There might be many classes that is using email service. And you have to go on make changes to every classes. And making every changes that adds up to your testing effort and all other efforts. It's like imagine your house wiring is shouldered directly into the appliances. Now if you want to upgrade your fan, you have to rip out your walls. Not ideal, right? You want things plugged in, not hardwired. Here is a big reason this happens. We are using the new keyword everywhere. As you have seen, with this new keyword, user service is tightly coupled to email service. Basically, user service has made the decision of what to use inside itself. And that's not its job. So, what's the problem with that? Number one, we can't easily swap email services for another service, like SMS service. If you have to use SMS service, you have to come to user service class and make changes here, right? That is what we want to avoid. That is the problem when we have tight coupling. We can't easily test user service with a mock. You might have realized whenever you have new keyword used inside the class, mocking this class becomes very difficult. And we are spreading concrete dependencies all over our code base. Imagine a code base where every class is creating its own dependencies using new. You will never know what's wired to what. Total chaos when requirement changes. Alright, before we refactor our code to follow the dependency inversion principle, let's pause and understand a keyword in the definition. That's abstraction. This word shows up a lot in the programming, and it's a very robust word. And it simply means hiding the complexity and exposing only what's necessary. Let me explain that in two ways, one real world and one code example. Think about a coffee machine. You press a button and boom, coffee comes out. You don't care how it heats water, mixes it with powder, or pours it. All of that complexity is hidden behind a few simple buttons. Those buttons are basically the interface and is nothing but the abstraction. You focus on what it does, not how it does. In programming, abstraction means defining a common set of operations while hiding the underlying implementations. For example, let's say we want to make a payment via UPI, credit card, or PayPal. Now, instead of directly calling UPI.MakeUPI payment or credit card payment, we define a simple abstraction, a common contract that says, hey, whatever you are, if you want to make a payment, just implement this method, pay. That's where an interface comes in. An interface in code is a perfect example of abstraction. It does not contain the logic, it just defines what should be done. Like this. So now our high level class, say either order service or transaction service which handles the main business, doesn't need to know how the payment is actually done. It just says, hey, I will call pay on whatever payment method and payment should happen. That's the beauty of abstraction. The details, whether it's credit card or UPI, are completely hidden behind that interface. That's also the power of coding to a contract. That's also the power of coding to a contract. So now I believe abstraction is clear. Let's go back to our code and see how we can use it to fix our tight coupling between user service and email service. Let's introduce an abstraction to notify the user. So as discussed in programming, abstractions are mainly interface. So let's create an interface. What name can we give? Let's call it iNotifier. Let's have a method called notify. Let's implement this in our email service class. Now let's change the user service to depend on the interface. This instance is not required now. Let's create a variable of type iNotifier. Let's create a constructor. Let's take iNotifier. That's it. Now, instead of email service, we will call sendMail via notifier. Let me write the code to call it from the main method and show you as well. So what we are going to do here, iNotifier equal to new. What do we want to use? We want to use email service, right? Email notifier. Let's pass this notifier to user service and call register user. That's it. Now you can see the user service just says, hey, I need something that can notify. I don't care how it does it. Let me build it. Okay, build got successful. Now user service just says, hey, I need something that can notify. I don't care how it does it. This makes it flexible, testable, and future proof. It's like calling a cab. We don't build a car each time we need to ride. We just say, I need a ride, and someone brings you a vehicle. That's what we want in our code too. Tell the system what you need, not how to make it. Now let's say you want the system to notify user via SMS instead of email. You don't have to touch a single line inside user service. All you do is this. I notified instead of email service, you will send SMS service. Definitely you have to create this class and implement iNotifier. The user service code will stay exactly the same. Why? Because it never cared how notification was done. That's the magic of depending on abstraction. And that's what the dependency inversion principle helps us achieve. So let's pause for a second and connect this back to the definition of dependency inversion principle. High level modules should not depend on low level modules, both should depend on abstraction. In our case, user service is the high level module. It contains the core business logic. The email service is the low level module. It handles the actual delivery of notifications. Before, the user service was directly dependent on email service, right? With new keyword. Now it depends on iNotifier, the interface, and abstraction. And email service also implements the interface, abstraction. So it means the high level module and low level module both are dependent on abstraction now. Or we can say they are both connected only through the abstraction, not directly to each other. That's exactly what the first part of dependency inversion principle is all about. And we just made it happen in our code. Now let's see the second line. Abstraction should not depend on details. Details should depend on abstraction. What does this mean? You know what's the abstraction now. Can you guess what does this mean? This simply means your interface, that's abstraction, should stay stable. Your concrete classes should plug into it, like email service notifier, tomorrow perhaps SMS notifier. It should not be the other way around. Like I have created SMS notifier, you can have different notifiers plugged into it. For instance, push notifier, WhatsApp notifier. As long as they implement iNotifier, as long as they implement iNotifier, the system doesn't need to change. This is powerful for a reason. You can replace parts without breaking others. Your code is easier to test, just pass in a mock. You know, right? When you're using interface, you can mock it easily. It's much more flexible. It's much more scalable. You can plug and play new features. Okay, now let's quickly discuss what can go wrong if you don't follow DIP, and then we'll wrap up the video. Let me tell you a real-time scenario that I have seen in one of my projects. In one project, the business logic was tightly coupled to file input-output operations. So when the team decided to move from file-based system to a proper database, they had to rewrite the entire core module. They couldn't do it piece by piece. They had to stop and rebuild everything. Time lost, money lost, trust lost, right? That's the cost of ignoring this principle. So to wrap it up, dependencies are natural, but how you handle them makes all the difference. Don't hard-code concrete classes into your core logic with new keywords. Depend on interfaces, that's abstraction, and let the details be swappable. That's what the dependency inversion principle is all about. Once you understand this, it will definitely change the way you design system forever. Hope that made things clear and simple. If you like this breakdown, make sure to check out the rest of the Solid series. I have already covered SRP, OCP, LSP and ISP. And if this helps, give it a thumbs up and subscribe if you haven't already. I will see you in the next video. Thanks.